Okay, well, welcome everyone. I appreciate everyone joining. My name is Mary Ann Stokes. I'm Director of Marketing for the FEMAP product line here at Siemens PLM Software. And we are thrilled to join up with Engineering.com in presenting this very, very interesting webinar series called Overcoming FEA Roadblocks. Today's presentation, this is the second of a three-part series that we're concentrating on in this Overcoming FEA Roadblocks. And actually, specifically today, we're going to hear from our director, Siemens PLM Software Director of Software Development. His name is Mark Sherman. And then we're going to have a question and answer period. So really looking forward to hearing any questions that you may have. The way we're going to work this is you're going to basically submit your question anytime throughout the webcast. To ask a question, what you do is you type your comments in the Ask a Question box and then press Submit. And we'll do our best to answer as many questions as possible within the time allotted. And then if we can't get to it, we will get to it post-webinar. Also, just a couple of notes here that in your resource list on your webcast interface, there are 2 case studies available for your viewing, as well as a link to the FEMAP 45-day free trial. So I encourage you to download the case studies and to look at the link up to the free trial. Finally, if you experience any technical difficulties during the webcast today, please click on the help icon at the bottom of the webcast interface for troubleshooting tips. And now I'll pass it over to you, Mark.
Thank you. Thank you very much, Mary Ann. Again, my name is Mark Sherman. I've been working on the FEMAP software and FEA in general now for about 25 years. I'll be walking you through our second webinar in our series on overcoming roadblocks and finite element analysis. The first one's available for replay and kind of covered just accessing CAD data and some of the challenges you might run into there, and also working with CAD data and cleaning that data up. Today's the second webinar, and we'll be talking about making a finite element model that's actually useful. This will get down to some of the roadblocks you can find with, first of all, meshing, creating a quality mesh, and then actually getting the model out and running it in one of the supported finite element solvers. So as an overview, we're going to talk about just an introduction to simulation in general, about why people use simulation, and obviously to improve product design. But then we'll move into actually creating FEA models that are useful. And some of the key things we'll go over is mesh control and mesh creation. Obviously, all these models require a mesh, but there's actually some pretty serious considerations that have to be given to element quality to make sure you get good answers. And then we get on to finalizing your model, which is basically putting on your loads and boundary conditions to accurately reflect the real-world loading and constraints your product might find. And then finally, we'll talk about moving those results into a solver so you can actually run the analysis and get the answers. All right, next slide. Why use simulation tools? And a lot of you on the phone call may already be familiar with finite element analysis, but we'll go over this. Again, one of the most important things to everyone is saving money and saving time. And by using finite element analysis, one thing you can do is actually use virtual testing. It's expensive and costly to build prototypes. The turnaround time is very slow. It basically, with virtual testing, you can turn around, many more iterations on any type of design cycle. You can actually use it earlier in the design cycle. The other big use of simulation tools is to understand how your part may fail. And obviously the goal would be to prevent that failure, which in the end is going to reduce any type of product recalls, even costly lawsuits and things like that. But it saves you time, saves you money, and also saves your company reputation if your parts aren't failing in the field. Another major use of FEA is optimizing your design, reducing weight, changing materials to a different, less expensive material. Huge cost savings can be realized here. Weight reduction, obviously, steel, plastics, everything's expensive. The less you can use, the more money you can save. And as we talked about on even the virtual testing side, iterations in your design. So trade studies are really important. You can actually, with FEA and virtual prototyping, you can work your way through a significant number of design iterations and studies and iterate in on a better design and make a better product and basically, again, save you time, save you money. There's a nice quote there from McDrill Technology talking about how material usage was key to their business and how using FEMAP and NX Nastran has given them a competitive advantage in their industry. Not only can we tell you those things, we kind of looked at FEA and from our own past and our understanding came up with those key issues. But the Aberdeen group actually went out and queried engineers and people using software of this type and said, hey, why do you do it? What are your objectives? What are your strategies? And these are the top 3 items that came from them. And it was reducing development time, improving product quality, and again, lowering cost. So, I mean, these are what resonates out in the field. This is what people want to realize from FEA. And then the interesting thing I found out here was to evaluate the more design iterations at an earlier stage and bring it more forward in the design process. A lot of times FEA is, in the past, has been a kind of after-the-fact type analysis where the design is set. You're just going to go verify that it's strong enough, but at that point your chance for affecting design and making changes and saving money up front are really limited. Another nice quote there on FEMAP and NX Nastran. So what's the process look like? In general, as we talked about in webinar 1, your geometry probably comes from a 3D CAD system. In today's times, most people have access to some type of 3D CAD system. You're going to bring that geometry into your FEA tool. In the case of the FEMAP product that we're telling you about today, we can bring in CAD geometry from just about any CAD system, and also bring in STEP and IGES and Parasolid, some of the more neutral formats. Once you get that data in, you have to accurately apply your loads, accurately apply your boundary conditions, create a mesh, and we're going to talk today about creating a really good mesh to get the best answers you can. And you also need to define material properties. The next thing is setting up your solutions and go out to a solver. Once these solvers run, and these are black box programs that basically take the input files and run and bring back the displacements and stresses and such that we read into FEMAP to do the post-processing work. And the final thing you can do is get that knowledge back to CAD, so once you understand your design, you understand how it performs, then you can update your design to make it better. We set up this little road, just kind of illustrating that the goal is always to get from that geometric model or your product definition down to an effective analysis. So some of the roadblocks you might find in this middle stage are actually creating your mesh, is you're going to need a FEA tool that has a deep enough set of functionality to accurately model your real-world product. So there's within your FEA tool, most products now have your basic element types, your tetrahedrons, your plates. But a lot of times you need to move in some more specialized element types. You might need to work in this more specialized meshing. You need to have a very deep toolbox available to you so that you can accurately model your products. The second roadblock you might fall into is just the ability to put your loads and your boundary conditions correctly. Applied force and applied pressure most programs can handle. But if you have a time or temperature varying type load, your product FEA pre and post processor needs a little bit deeper. Your solver needs to be a little bit deeper. There's some neat stuff in FEMAP we'll show you where we can use the results of one analysis and map it onto a mesh of another analysis to transfer CFD pressure results or thermal data from one model to another. And finally, the challenge you might reach is you can model all that stuff, but then you need to get it out to an ANSYS, an Abacus, an LS-DYNA, or a Nastran, and you need to get it in there correctly. These codes are very rigidly defined input formats, so you got to make sure that those numbers and all the stuff you think you created in the pre-post processor are getting out there correctly. Excuse me. So what we're going to do today for these roadblocks is we're going to introduce you to our product FEMAP. FEMAP is a standalone pre and post processor. FEMAP is not a CAD system. It's not a CAN system. It is a dedicated tool that all we do is build finite element models. We have a very tight integration to numerous finite element solvers, but our company Siemens actually owns its own Nastrans. We have a very tight integration with the NX Nastran product, and Nastran has a long-term history and reputation of quality in the FEA industry. FEMAP's a very open product. As we discussed a little while ago, CAD independence, we can bring in CAD models from just about anywhere. On the solver side, even though we have our own Nastran, we support other Nastrans. We support ANSYS, Abacus, LS Dyna. And then we also have a lot of integrations to third-party products. There's products out there that do electromagnetic simulation on top of FEMAP, fatigue simulation. It's a wide-open system with an application programming interface that people can access and create some pretty fantastic additional functionality on top of FEMAP. And we've always tried to keep it easy to learn, easy to use. It's a native Microsoft Windows product. It's been Windows since Windows 3.0 in 1992. We moved to Windows, so that ease of use has been there, and a Windows-based, Windows native. And we try to make it as intuitive and the processes as easy to follow as possible. All right, the tough thing, roadblock number one is sometimes you got to get a good mesh. And why do we want a good mesh? It gets down to accuracy. Better shaped elements, in particular in areas where there's high changes in stress, so where the stresses really matter in your stress concentrations, distorted elements can lead to less accurate results. So you want to have a lot of control over your element shape, sizing, and make sure that you get good quality elements right where you need them. Badly shaped or poorly shaped elements can even prevent these solvers from running. So some of the solvers, they're hard-coded. If an element comes in, it's so poorly shaped, it won't even run at all. You get no results. Even if that poor shaped element's in a part of your model where the stresses aren't changing a lot, it doesn't matter. You're still not going to get a result.